I don't think we're gonna come to an end to that conversation.
No, probably not.
And that's fine. That's a good conversation to have. But anyway, dear Father, we thank you for this day. Thank you again for your creation that you've allowed us to study. Help us to understand a little bit more about it today, Lord. In your name, I pray, Lord Jesus. Amen. All right, so I'm going back to lecture 11. I mean, we got all the way to lecture 12, but now I'm dragging you back to lecture 11. At the end of lecture 11, I talked about this, but I didn't actually do it. So let's do it. All right. So we're going to glue a charge density function of theta over the sphere, radius r, and we want to find the potential inside and out. All right. So in this situation, we know the potential is continuous, right? As we've explained, that's inescapable unless you want to have infinite. Anyway, the potential is continuous. So anyway, yeah, inside, I can't have the b terms in the general. Remember the general setup. Let me go back to the start of chapter 11. Chapter 11 is the start of lecture 11, which actually we derived this in lecture 10, right? Lecture 10, the result we got to was that the potential, if we have independence of the angle phi, we can write the general solution to Laplace's equation as the sum of these, this kind of radial function times this particular kind of angular function, namely the Legendre polynomial. And it just so happens that as we apply that to example 4 over here, as we think about the case inside the sphere, that would be where r is equal to 0, and as such we can't have the b sub L term, because if we did, this piece here would blow up, and that's bad. Because we'd like our potentials not to blow up when there's nothing, there's no charge there, there's no reason for it to blow up, right? It's just whatever, empty space, I think. Yeah, empty space. And because I'm not given any other charge. This is the only place there's charge here is on the surface of the sphere. Okay, that's the deal. Anyway, so we got the b is 0 inside, but outside you need the a to be 0, because outside we let r go to infinity, which basically means we need to get rid of the other half of the Legendre solution. So it's a pretty cool problem in that we use half the solution for inside, the other half for the outside, but they have to meet in the middle by continuity, right? Like when we put little r equal to big R into these two expressions, they got to match up at the at the sphere. All right, and so by continuity of the potential at r equals to r, we get the relation between the a's and the b's as such. We get b sub L is a sub L times r to the 2L plus 1. And okay, but then we're given that there's this charge density, sigma not the theta. And remember, a localized charge on a surface implies a discontinuity in the derivative of the potential, which of course is the electric field, right? There's an electric field which is, sourced by this charge that's distributed at the surface. Well, I mean, I say sourced, but it could be the electric fields are going into. It could be a sink or a source, depending whether the charge is positive or negative, right? Field lines could be ending or beginning on this surface. But then, when we calculate the r derivative out and the r derivative in, we're using the different formulas I have up here, right? Like, I'm differentiating the outside one. When I do that, I get minus L plus 1 divided by the power L plus 2, because I've got the reciprocal term, so I'm differentiating the reciprocal term there. I get the reciprocal derivative. On the other one, I just get L times r to the L minus 1, because I started with an r to the L, and I evaluate at r equals to r after the differentiation. All right? But if you look at this and you use that equation right here, you can collect these terms together. Why have an a and a b when you can just have an a? So that gives us this. All right? So we get, if you look at it, you can see it. It's not too hard to see. There's this b sub L's got the r2 to the L plus 1. So when you put the 2 to L plus 1 here, it simplifies back down to L minus 1. Because you've got L plus 2 in the denominator, you're subtracting L plus 2. 2L plus 1 minus L minus 2 gives you L minus 1. That's how that power works there. And then, of course, you've got minus L minus 1, and then a minus L, which gives you like minus 2L minus 1. But notice there's a minus over here as well, so we're multiplying the whole thing by minus 1 to get this 2L plus 1, and the 1 over epsilon naught, sigma naught over here, which is ever so very lovely. So great. Then, going on, we take that equation that we just had, and we multiply both sides by the mth Legendre polynomial times sine theta, and integrate from 0 to pi. Aw, man. Use your imagination. There's a white pi. There's a white pi right here, 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 and also here. There's a white pi. If you look really carefully, you can see the white pi. Okay, good. Very good. And as such, when we pass the integration and sign the summation, and we use the orthonormality, well, not normality, but the orthogonality of the Legendre polynomials relative to this integration, we get ourselves a Kronecker delta Lm, 2 divided by 2L plus 1. The 2L plus 1, it'd be canceling like so, and it just leaves you with a 2m a sub m. I'm keeping the m, because the L is summed over, so let's keep the m. M is free. Free! And then, whoa, cool. Somehow I'm more relaxed now, but it's catching. Huh. Maybe there's some sort of like spiritual plane on which our auras are connected, and when you crack your back, you crack my back.
Maybe.
It's like some kind of, that's what I was talking about. It's not an illusion, that's the reality. My friend, every time I give him some kind of fact or quote or something from like the Tucker Carlson show, he's always like, but he said aliens are real and they're running the government. And I'm like, well, demons are aliens, and there are definitely people who are satanically influenced and running parts of the government, so I don't see it's that bad a statement. I don't know. I need to hear the quote like directly, Anyway. Sorry, I have been in at least 2 or 3 Sunday schools where the question has been asked, like, do you believe in aliens? And I've been like, yes, I believe in demons. They're life forms other than human that exist in our physical plane of reality. So yes, I believe in aliens. They're demons.
Why can't angels be aliens too?
Exactly. But it's more shocking when you say demons.
Yeah.
So, but yeah, same thing, right? And of course there can be different kinds, right? But it's always like, it's a little bit disturbing to be like, the Sunday school teachers are like, I never thought of that. I'm like, but you're asking this question. How can you not have thought of this? Like, it's because they only can operate in like the world of like X-Files aliens. They have to be like the goofy gray ones or the shapeshifters, or you guys don't even know what X-Files is. What am I talking about? Oh, you do?
A little bit.
Okay, good. Very good. Very good. Nope.
Shame.
There's a 20% chance today's students know X-Files then. That's what I'm hearing.
Yeah, it probably does. A little odd.
A long time ago, there was something called television. And we used to watch these things called shows on television. They came on a specific time of the week. You had to like plan your day around this. You would tune in on a certain day at a certain time when you watch the show. Later, there was this thing called Netflix that was invented where you could get discs through the mail. They would put into this thing called a DVD player. And you could watch whole seasons after but you'd have to wait till they mailed you the next season. So anyway,
What do you hear about Redbox?
oh yeah, the Redbox. Yeah, Redbox killed Blockbuster. But anyway, man, I haven't gotten Redbox in like, wait, does it even exist now?
I don't think that movie.
Okay, I was gonna say I haven't gotten that in oh, that's right, they're gone. It's like I control reality through my consumer choices, but I digress. Anyway, so after we do this thing and we calculate the a sub m, lo and behold, we got a formula for the mth coefficient in terms of integration of the given surface charge density over the sphere. You put that thing back into here, and there you go. That's the potential that will produce that charge density on the surface of a sphere. I mean, this works for arbitrary charge density of theta. But we're particularly interested in k cosine theta today. So let's do that. That integral becomes super easy to do. See, if you just have, your formula, if I put k cosine theta, that's just P1. But you know how this works out. Well, this is just Kronecker delta, M1 2k divided by 2 epsilon naught r to the m minus 1 divided by 2 m minus 1. But this specifically is just, it's only non-zero when m equals to 1, which gives me a 3 here. So we get k over 3 epsilon when m equals 1, and we get 0 otherwise. And so this particular potential, in this, if you have that charge density, k times cosine theta over the sphere, right, which means that you've got a positive charge density up on the top, where theta is 0, and you got a negative down here, where theta is around pi, and you got 0 on the edges, right? So it's the kind of induced charge density we sort of expect for like a uniform, like if you had the electric field that's pointing up, this is the kind of charge density you might induce on a sphere, right? Negative down here, positive up here as the electric field's pushing the charge up like that. Okay, so there it is, all right? So let me just write that down. V of r theta, k divided by 3 epsilon naught times r cos theta for r less than or equal to r, and then k r cubed, big R cubed, divided by 3 epsilon naught r squared cosine theta for r greater than or equal to r. Can you guys recognize what kind of potential we're looking at here in the context of beyond the sphere? What is that?
Slowly decay.
Well, it depends on r squared, right? So is that a Coulomb potential? Like, what kind of potential are we looking at there? Modulated Coulomb. Whoa. Well, the Coulomb just had 1 over r, right? This is 1 over r squared. This is a dipole. This is literally the pure dipole. Right here. This is the pure dipole potential. All right, so that was the end of lecture 11 that we talked about this, but we didn't actually work out these details, obviously, right? Yeah.
Does this mean that if you were to use a pure dipole near a sphere that would induce that kind of a surface charge?
Yes. Like if you put we'll see. We'll see. So you guys don't mind if I don't write everything out today, I hope, because I'm very tired. I don't know why I'm so tired, but I'm very tired. Not enough coffee, maybe that's it. Maybe I'll regain my strength by the end of lecture here. So lecture 13, we're finally properly in it. Insulators have positive and negative charge, right? When they subject them to an E field, the charges are drawn apart and the result is the creation of a dipole. So, you can kind of picture this. I will attempt to picture it. You've got, some positive and some negative. I use red for positive, blue for negative. And suppose like they're all kind of stuck in this solid, right? And maybe you're making an E field like this, right? And so what might happen is the positive charges get pushed up here, so to speak, right? And the negative charges maybe get pushed down here like that, And okay, like the more complete picture of it is something like it's a whole lattice of molecules, right? Like a whole bunch of atoms. And if you could zoom in, it would look more like, let me just kind of zoom in to a little bit here. And so maybe the atoms are like this. minus, so the minuses are down here, and then plus. And so each minus plus pair corresponds to like a particular little atom, all right? You can think of the whole solid being created by a bunch of atoms stuck together like this, right? And the presence of an electric field, it's going to make the atoms align and go such that the negative part of the atom goes down and the positive goes up, right? The negative part being the electron cloud, the positive part being the nucleus, let's say. And this keeps happening, right? And if you look at the totality of the object, right, you get, you know, this kind of alignment in molecule after molecule after molecule, right? As these align with some external polarizing electric field, right? What's the net result is that, you know, I can draw like this is just the end of the story, right? It's plus minus. I'm drawing it as if there's like 10 atoms across this object, which is pretty ridiculous, but you get the idea. All right. So if the electric field, you know, makes these atoms that are kind of stuck in place, because we're talking about an insulator, the charges aren't really free to move. They're just kind of stuck in that locale, right? Then that's the situation. And what ends up happening is you have a net excess of negative charge down here and a net excess of positive charge up here. And what that means is overall, the object behaves like a dipole. Assuming it's neutral for the moment. A little bit later in the chapter, we also consider the possibility that there's also free charge to move around in the matter, all right? But let's just complete the discussion here, starting with the atomic polarizability. So Griffith starts by just saying, well, let's think about a single atom and talk about the issue of polarizability of an atom, all right? So I'm getting ahead of the story a little bit with my pictures down there because I think that's kind of more interesting, but I really put the cart before the horse here, my bad. But so he really just focuses on explaining just one of these guys next. So he's like, an atom crudely consists of a nucleus with a positive charge Q and an electron cloud with charge minus Q. For the E field not too big, the electron cloud remains roughly spherical. And so you can kind of picture, well, here's the picture. So the picture is that we have, here's the undisturbed atom. You've got this electron cloud, it's roughly spherical around the nucleus, all right? And once you apply an external electric field, then what happens is the nucleus gets pushed that way a bit, all right? But then, if you think about it, there is got to be kind of like a balancing between the electric force due to the negative electron cloud versus the external electric field, which is displacing the nucleus, all right? And Griffith argues that if the E field's not too big, then the electron cloud's still roughly spherical. But we know the electric field for a spherical uniform charge distribution is linear from the center, right? So I can write just QD over A cubed because that's like the distance D from the center divided by A cubed. That's the radius of the sphere. So this is the formula we derived for a uniformly charged sphere using Gauss's law a couple weeks ago, right? And I put the minus x hat here because obviously the negative electron cloud is going to be pulling the positive nucleus that way, right? And if not for the external electric field, it would be successful, right? We'd be back to that picture. The nucleus stays in the middle. That's how things balance, right? You got the negative electron cloud outside. You got the positive charge inside. much more to say here about quantum mechanics and stuff, but let's not. So, all right. Anyway. So this field must balance the external electric field, which gives me E equals to this. And then I solve for that. I get P equals QD, which is, I'm defining QD there. Well, I'm just pointing out that QD is equal to this, but that, he points out that this quantity is the alpha, the atomic polarizability, and that's equal to 4 pi epsilon naught a cubed, which is, by the way, 3 times epsilon naught times the volume of the sphere, because the volume of the sphere, the electron cloud, that is 4/3 pi a cubed. So, and Griffith says that this is accurate to within a factor of 4 for most simple atoms. All right, and he's got a table of values for this, so that's kind of neat. All right. So great. But what about a material comprised of not just one atom, but like a whole bunch of them, right? So like that concept of atomic polarizability pretty much just exists in the start of this chapter. It's just kind of like a introductory discussion to get you understanding the basic physics that underlies this. This is what we're really interested in, is like bulk objects, like I was trying to, draw down here. So, all right, so we introduced the polarization, and that is defined to be the dipole moment per unit volume. All right. Now, this assumes that there is a regular direction to the dipoles, right? You could imagine objects which had dipoles, some pointed this way and some pointed that way, and all every different which way in between, right? And in order to properly describe that, you'd need a tensor. You'd need a much more complicated object than just a simple scalar in a direction. But we are assuming that the objects we're talking about today are simple enough that the dipoles are all aligned, all right, nicely, and that's what we're thinking about. So, but we should be careful even with that, because there are two different fields to consider. There's the field which is necessary, right, in order to cause the polarization. In other words, if I started with an insulator, right, and the atoms are just every different which way, according to whatever, lattice describes the physics of, the collection of molecules, the chemistry, whatever it is, that would be different than once I apply the electric field, it makes them all align, and it sort of freezes in some kind of polarization. Now, whether or not that's frozen in permanently just by some materials, if you apply the electric field, it lines them up and they just kind of stay like that. Other ones you have to keep doing it. It's like it's a complicated business exactly how polarization is maintained or not. And we're not answering that question at the moment. Today we're mostly just looking at the idea that we're given a polarization of a particular particular chunk of mass, and we want to understand really question 2, which is the field is created by the polarized material due to the polarization. In other words, I want to understand what kind of electric field we get as a consequence of these pluses being up here and these minuses being down there. Like, what happens from that? All right. And so to do that, we need to just do a little bit of soul searching here. We worked out the potential for the dipole the other day was p dot r hat over r squared. Now here, this is like q times d. Well, excuse me, this is the perfect dipole. So, technically speaking, this is what it is. But anyway, if we say that the dipole I'll get the words eventually here, but the polarization is the dipole moment per unit volume, then infinitesimally I get that dp is the polarization d tau, right? So I can find the net dipole. Well, excuse me, I can find the potential due to the dipole dp by simply integrating P, this is the capital P, right? I've always put the foot on it. That's the difference. You see the difference? My big P is polarization. This is the dipole moment, the infinitesimal dipole moment that is present in the volume d tau. All right, so I need to do this integral is what it boils down to, right? That looks kind of scary, right? It's actually like pretty, it seems very intimidating. Like, how are we going to make any kind of theoretical progress on that at all? Well, here's how. First of all, we need to tilt our head and squint and realize that if we look at r squared, we can, write it like this or like that. And then if you calculate the partial derivative with respect to the prime variables, you get this. But then that gives me that the gradient of 1 over r is like this. And a little bit more math, but that implies that the gradient prime of 1 over r is just script r hat over r squared. So in other words, I can trade this script r hat over r squared in the integral for a gradient of 1 over script r, where the gradient is being calculated with respect to the coordinates based on the source point. Notice that this is a source point derivative as opposed to a field point derivative. That's important because the integration is done over the source points, not the field points, right? So, as such, we're able to, and I probably should write this out, but you'll forgive me if I don't today. So 1 over 4 pi epsilon naught. So I trade out this r hat over r squared for, delta prime of 1 over r. So going from here to here is just that product. Remember that product rule you guys proved in homework 1? So like the divergence of a function times a vector is the gradient of the function dot the vector plus f times the divergence of the vector field. That's still true for the prime gradient. All right, still true for the prime gradient. And as such, I can trade this piece, which is kind of like this piece, I guess, for that piece minus that piece. So I do the gradient of 1 over r times p, which is this, minus 1 over r times the gradient of p, which is that. All right? So in other words, this, like Griffiths will call this integration by parts, and he's not wrong. I mean, what is integration by parts? It's just using the product rule inside an integral in reverse, right? That is what integration by parts is. So anyway, that's how to understand physicists when they say they're using integration by parts, okay? If you start literally looking for the u and the dv in the sense of calculus 2, we're going to be here a while, Sorry. Anyway, cleaning it up a bit, I separated these like so. And then I think I switched markers because this marker's too stupid. So what we got here is this. You see, what did I do? What's this step right here? Notice that I've traded the volume integral for the surface integral. This is the divergence theorem, right? So the divergence of this vector field is the flux integral of the vector field over the area of the surface of the volume. All right, and over here I didn't do anything except just write it again. But anyway, if you look at it, we've got 1 over 4 pi epsilon naught, this business minus that business, and well, this is effectively a surface charge, which we're going to call the bound charge, sigma b. And this is like a volume charge. We're going to call this the bound charge, rho b. Now, the bound charge, rho b, you cannot see in my hokey-pokey pictures down here. I do not currently have the pictorial skill to draw you a picture of a faux atom, a bunch of plus minuses in such a way that I illustrate the divergence of these being non-zero. I haven't thought, maybe it's not that hard either. I haven't thought about it too much, but anyway. How do you picture divergence? But, so, here's our definition. The bound charge due to a polarization, all right, so you have a polarization over some given volume. So if we take the dot product of the normal to that volume with the polarization, that gives us the surface charge density, the bound surface charge density. And likewise, rho sub b is the divergence of the polarization. That gives us the volume charge density due to the polarization P. These are bound charges in the sense that they're like somehow or another related to the particular structure of the atomic structure of the matter which we're talking about. These charges can't move around. They're just being kind of contorted and stretched in bulk in such a way that we have the effect effectively, despite the fact that the atom overall is neutral, the object overall could be neutral, there's a net accumulation of positive and negative charge at different places, which gives rise to these so-called bound charges. All right? And so theorem, to find the potential for a given polarization P over a volume V, we can calculate the bound surface charge, P dot n hat, and the bound volume charge, rho B, by the divergence of P like this, and then we can proceed as before to write the potential due to the given charge distribution. Because we already know what to do, right? If once I give you guys, here's the surface charge, find the voltage, find the potential, we can do that, right? We did that started today, so we can still do it now. Even though the motivation for the charges is now different, right? The motivation for the charges being where they are is that there's this polarization and we're finding the bound charge as a result of the normal, the dot product with the normal or the divergence. So, how about this? What's the electric field produced by a uniformly polarized sphere of radius r? Well, let's put the polarization in the z hat direction for good measure, because we already done a lot of math like that. And for convenience, P is constant. Then the bound charge density is Pz dot n hat, but n hat is r hat because it's the sphere we're talking about, right? The radial, r hat is the normal to the sphere, right? And what is z hat dot r hat? Well, z hat r hat is cosine theta. And now we're back to Shane's comment. We have found the charge distribution due to the bound, the bound charge distribution due to a uniform polarization is exactly a constant times cosine theta for a uniformly polarized sphere. But we already know how to solve that. So we just put P equals 2K, and there is the voltage, the potential, due to a uniformly polarized sphere. And then we can calculate the electric field from the potential, right? Take the gradient. And so the electric field due to the polarization inside the uniformly charged, uniformly polarized sphere is given by minus the polarization divided by 3 epsilon naught times z hat. That's what you have within the sphere. So like the electric field's pointing down. And then for, oh man, I don't know if I scanned, I'm not sure if I have a scan of that picture or not. Oh, I gave it to you guys last time, the sheet, the handout. We should look at that soon, I think. Yeah, maybe that one. I'm not sure this is the right thing to look at yet. I think it is. I gotta, yeah, the dielectric sphere and the uniform. Well, we don't know what D is yet. We'll talk about that next class, guys. That's the so-called. Well, we'll talk about it next class. All right. There's another competitor for the electric field that's called Big D. Well, it has another name, but again, next class we'll talk about that. But anyway, so the electric field due to the polarization is just this. But on the other hand, outside the sphere, if you look at it, we've got this formula, but you could also rewrite that as P dot r hat divided by r squared. And it's as if there was a single perfect dipole at the origin, and the dipole moment, big P, well, little p actually, is 4/3 pi r cubed times big P. So big P is, dipole moment per unit volume. So I take dipole moment per unit volume times the volume, which is 4/3 pi r cubed, and that gives me the dipole moment of this uniformly polarized sphere. And that's what happens outside. It is as if it's just a giant dipole at the origin, Yeah.
What do you mean by dipole moment? What does that mean?
What do I mean by dipole moment? Well, we defined that last class. I mean, it's part of the multipole expansion. It is an idealization. So the physical dipole literally means, plus q minus q, distance d apart, right?
Yeah.
So we had plus, minus, right?
Yeah.
And, the distance d. So we talked about p equal to q. There's a plus q here, there's a minus q here, right? So qd vector, this is the dipole, physical dipole, right?
Yeah.
Perfect dipole obtained as limit qd, qd equals to p as q goes to infinity and d goes to 0. So it's an idealization. In some sense, what the perfect dipole says, if you look at the perfect dipole field, all right, what it's saying is that it doesn't matter how big the dipole actually is. No matter how far you zoom in, you can't see the internal structure. So like, if we look at dipole fields, I'm going to see if I'll try. So the electric field in this situation looks like what? Like this, right? And then one of these, and one of these, and one of these, and one of these, one of these, right? And then the same. Like that, right? That's the dipole field. But if I put them really close, like that, and I keep putting them closer and closer together, that is the electric field due to the ideal dipole. And so, words. I have the stupid formulas on top of my head. Goodness gracious. Well, we've worked out the potentials for these different things, right? But that's the distinction. Like this is, in that limit, it's the perfect dipole. But again, I think really what it says is you can't actually see the difference between the minus and the plus. It's kind of in principle there, but yeah, you don't actually. All you know for sure is that the product of the charge and the distance between the separated charges is p. You don't actually have access to the q's that are separated. And yeah, I don't know if that's a satisfying answer or not. This always bugged me when I was in the course. Like, what on earth is a dipole? I have always had intuition for a monopole, but like dipole to me was always a little bit mysterious. Yeah. But it's just the next step in the story of the multipole expansion. So that's the neat thing, is this uniformly polarized sphere. It's as if it's just a perfect dipole at the center of the sphere, where the dipole moment is the totality of the spread out dipole moment per unit volume, as if it's just at the center of the sphere. Just like it's just so much similar to like stories we've heard before, right? You've got charge spread out uniformly over a sphere, right? And you get outside the sphere, it's as if the whole charge is at the center of the sphere, and it's just the Coulomb charge of that. Like, this is the analogous result for dipoles. Oh, I'm fresh out of notes. So, if I had my book, we could try to work a problem, I guess. Actually, I have held you guys like 5 minutes over multiple other times, so we can stop here today if you'd like. Sound good? All right. Unless you guys got questions. The next thing up is to define I think it's called the displacement, but let me not say more because I need to make sure that's half the battle is learning what the name of the stupid thing is. Anyway, I'll see you guys Wednesday.